For part B of this question, we are given the fact that now we're at this cruising speed. So cruising speed means constant velocity, constant velocity in this case. So what that tells me is that at that cruising speed, the net force is zero, no acceleration anymore. So the force of the motor is going to be equal to the weight force, which is m times g. So I'm going power is work over time. Power is force times delta x over time. Now, there's another equation for power that you may have gotten from the reading, but it basically is shown here already, right? Because if I do some just very basic algebraic rewriting, that's saying power is equal to force times delta x over t, where delta x over t is velocity, average velocity. When v is constant, then power can be written as force times velocity, because that velocity is delta x over t, which is f delta x over t. So in this case, my power would be equal to the force mg times the velocity v. And that's it. That's my solution. And then lastly for this part, the question says, if the elevator can only deliver this power, how long would it take for it to accelerate to a faster cruising speed? And the answer to this question is that it never will accelerate to a faster cruising speed because it will never be able to overcome that weight of the car to speed up even further. It'll just keep moving at that constant velocity of, in this case, 1.75 meters per second. So the answer to part C is never. It'll never get there, or infinity seconds. And then lastly, we have this electric motor of a model train, accelerating a train from rest to 0.735 meters per second. And we're given the mass of the train. Again, this is in grams, not kilograms. This time is in milliseconds. So we're going to need to convert those. But my givens here are V initial, V final, T, and M. So again, that power is equal to work over time. In this case, I'll have constant force again, so that's F delta X over T. In this case, I cannot use the F times V equation right off the bat because my velocity is unknown at this point. Like the velocity that I'm given is a final velocity. There are other ways you could do this. You could solve for the average velocity and then plug that in and do force times velocity. Or you could solve for the force in terms of second law, and then you could solve for the displacement in terms of kinematics and solve it that way. Effectively, they're the same math, just two different sort of ways to get there. So I'll do it the simple way. In this case, F equals the net force, right? The F motor, the electrical force, is the net force. So that's equal to M times A, or M times delta V over T. And for my displacement, delta X, well, in this case, I have constant acceleration. So that's going to be equal to the average velocity times time, or delta X equals V plus V naught over 2 times T. In this case, my V initial is 0. So my force equation is going to be F equals mv over t, because that initial is 0. And my displacement equation is going to be delta x equals vt over 2, because again, that initial is 0. So now all I need to do is plug that into my power equation, and I get power equals force, or mv over t, times delta x, vt over 2, divided by t. Time will cancel out on top, and I'll get my power is equal to mv squared over 2t. If you're paying close attention to this, you may notice that this is also the same thing as writing power equals 1/2 mv squared over t, or power equals the final kinetic energy over t. And that should make sense because power is work over time and work is the change in kinetic energy, right? So you could also solve it that way. Lots of different solutions for this problem, but ultimately you get that power as mv squared over 2t. And that is it for our video keys. Enjoy.